Hello, good evening, everyone. Am I audible?
Good evening. You are
Yes, sir.
audible.
Good evening, sir. You're audible, sir.
Yes, sir, you're audible.
Thank you. Thank you. So, okay, so today we are going to have open session for week 6 on week 8. Also, if you have any doubts in week 6 or even in week 7 or week 8, you can ask here. We'll try to answer those questions. And I planned some, I've had some set of questions, maybe 7 or 8 questions that I will plan. I'll ask you those questions and we'll go through the answers of those questions as well. So before that, if you have any doubts in any questions of week 6, 7, 8, you can ask. So probably week 8 is the one that the deadline is today, right? Today or tomorrow is deadline. So most probably you will have doubts in week 8. So priority is for week 8. If you don't have doubts in week 8, we can take questions from week 6 to 7. But otherwise, I can show my questions first, then you can ask your questions. So how you want to go, like, I mean, should I present or you should ask questions? Okay, so let's go with,
I have one doubt. I have one doubt.
yes.
So I just wanted to know that means like the programming assignments which are given in these weeks means week 1, week and all
Yes.
means are these programming assignments gonna be discussed in this meeting?
Not in this meeting, but we are planning to have some workshops for the programming assignments. I mean, programming part. So after the end sem, probably you will go through all the assignments before, along with the weeks, and in the last of that, we will having a workshop maybe after this term, or I'm not decided the date yet, but we'll go in that manner. I mean, we will decide some workshop. They will discuss most of the assignments, the programming assignments, and then we'll have an OPE for that. So that will give you a proper time. You can solve those assignments along with the weeks as well, and after the exams, depending upon your availability for the courses, you can choose both way. Okay, so
Sir,
that is the way we have planned for that.
sir, in one of the live session with Karthik sir,
Hmm.
it was discussed that even at the beginning of the course in the month of January itself, it was discussed that if needed, down the line we'll have one session per week for coding. So, in
But
last
initially we started, if you remember, we started doing the coding session as well, and we dropped the ideas after because their participants were very less,
no,
and
that used to be a part of these two sessions only, sir. What I am talking that the additional session for coding. So he said that okay, we'll figure it out. So after
okay,
that, I think you are taking content for week 8, so it was not discussed with him. So since there are only two instructors in for this course, so could you please discuss with him that what's the plan?
okay,
Because
okay. No,
because
no.
that workshop goes for 6 hours, only one workshop, right? After exam that happened last time also, but I don't know. I'm not sure how much that one workshop will help.
Okay, so that is okay. We can have workshop later. That is already planned, but not decided the date. Yeah, if you want along with the along with the weeks as well, that is fine with us as well. But for now, I am not sure whether I can do it. But definitely from the next time, I can take the programming assignment as well.
No, not today.
Not an issue.
I'm not saying not today, sir. And I'm saying that over and above these two sessions, we don't want to compromise on these two sessions because these are very much needed to have some theoretical discussion and the conceptual discussion. I'm saying that additional session because that on-demand session, right?
Hmm.
And Karthik sir
Hmm.
was in sync with the idea. He said, yes, we'll figure it out how to start.
Okay, okay. So I will discuss with him if we can plan any, I mean, some sessions. Then we'll definitely will have those sessions as well. Not an issue.
Yes, yes, yes. Thank you.
So yeah, someone was asking some doubt in week. I think Pranjal was asking.
No, sir. No, sir. My doubt was this only. Means like, do we have programming assignments to
Okay,
discuss in
okay,
the session
okay,
or not?
okay. So okay, so if you don't have any doubts, I think I should present my questions to you. Then probably later we can have the doubts as well. Okay. Can you see the screen?
No, sir, not yet. Yes, now it's visible.
Okay. So these are some questions, I mean 6 to 7 questions that I want you to answer those questions, and then probably we'll discuss solutions as well. Some basic conceptual questions, not very hard ones. So this is the first question. Question is, what is the effect of increasing or decreasing the risk parameter on the models? I mean, how it affect the models coefficients and the predictions, or say the performance. So risk parameter is lambda, right? So how it affects your model coefficient and prediction? So does anyone want to answer this? So this is your lambda, right? So how the lambda affect your model performance or the model's coefficients?
Reduces the weight vectors.
This is the weight vectors on increasing the lambda or decreasing the lambda.
Decreasing the lambda.
Okay, so you mean if I decrease the lambda, my weight vectors will decrease, is it?
Yes.
Any other answer?
Increasing the lambda will decrease the weight vector.
Okay, so we have two answers. In increasing lambda will decrease the weight vectors, and decreasing the lambda will decrease the weight vectors. So decreasing means it will try to shrink the weight vectors to zero, right?
Exactly.
So any other answers to this? How the lambda will affect the model performance and models coefficients? So this is very basic question, right? It's not very hard one. Okay. So, so how do you define the risk loss? How do you define the risk loss?
Sigma equal to 1 to n. Predicted value minus actual value whole square plus lambda norm w square.
So this is defined as x transpose w minus y, right? The norm of that. This is the squared loss, and then we add some penalty to this. The penalty is defined as lambda and norm of w square,
Norm
right?
of w square.
So this is called the risk parameter, right? So this is a hyperparameter. So what is the difference between parameter and a hyperparameter?
Hyperparameter is something which the user sets up, and the parameter is something which is learned from the model itself.
Yeah, correct. So
Like
parameter
the
is
model
something that
learns.
model
Model
it
learns.
learns using the training data set, right? And the hyperparameter is once that model cannot learn, it's the user defined parameters. So you have to choose by using cross validation techniques which one suit for your problem, right? So this lambda is the hyperparameter in this case, and these w's are the parameter, right? So how the this parameter will affect your weight vectors and predictions in this case, right? So this is your loss function in the rigid regression problem, and our ultimate goal is to minimize this thing. So we want to minimize this thing, right? So if you think this is the so I'm looking at the effect of this lambda on this thing. Let's assume I choose some values of lambda. Let's say I'm assuming lambda equal to 1 and some lambda equal to, let's say, 10 and lambda equal to 0.01. Okay, so I've chosen these three values, and I want to know out of these three values, which value will be best suited for my problem, right? So how I will find it. So there is cross validation techniques, like we will do k-fold cross validation. We train the models on some k-folds, and for another one fold I find the validation loss, and I do for all these three lambdas and choose the one which gives me the best validation loss, right? Or say the least validation loss. So in this case I choose, let's say it's 10, comes out to be 10, so I choose lambda 10. But what is the effect? If I keep on increasing, let's say I started my lambda at 1 and I keep on increasing my lambda value, then what will happen? What will happen to the w vector w, and what will happen to the training loss, or say the test loss? What they will affect? How they will be affected? Okay, so it's pretty easy to see here that if I keep on increasing this thing, and our ultimate task is to decrease this thing. So if I keep increasing this thing, I have to make sure that this loss keep decreasing. So I have to make sure that this weight vectors should decrease. Otherwise, this loss will go higher, right? So if I increasing lambda, my weight vector will shrink to 0, right? So that's easy to see here. If I keep my lambda increasing, then my weight vectors will shrink to 0, right? So higher the value of lambda, the less the most close to zeros values that W will have, right? So that is easy, that I can say. And what will happen to the training loss and the test loss? What about training loss and training loss and test loss? Is this clear? Whatever I'm saying, is that clear or not?
Both of them will decrease as well.
Both of them will decrease on increasing lambda, right?
Yep.
It need not to be true. So my claim is that the training loss will decrease. Sorry, training loss will increase and test loss may decrease. That is my claim. Can you argue on that? I mean, my training on increasing lambda, my training loss may increase. On most probably it will increase and test loss may decrease. So can you argue on that point?
Means we are basically modeling on the training set, right? So if
Yes.
you are increasing the lambda, means like we have to model in such a way that x transpose w minus yi, so that x transpose w minus lambda I uh, will means for example, means in training it should decrease, and as we have the test set, and we are means like we want to find that is this model suitable for the training, for the test one, it will decrease on test as well, means like according to me, on in both the training loss will be decreasing, training and test.
I think the training loss will increase and test loss will decrease.
Yeah, so answer is training loss will increase, test loss may decrease. It may not decrease, or it may increase, may not increase. So they cannot say with certainty that the test loss will always decrease or always increase. But the most probably is that the it's very likely that test loss will decrease on increasing lambda, right? And that's our goal, to use ridge regression. Otherwise, we can use the simple one as well, like the ordinary least square method list. So
A bit define training loss and test losses just once?
sorry.
Can you define training loss and test loss just once?
Define instrument, that is just the we make the prediction for the training data set and find the loss, and similarly for test data set we find the predictions using those weight vectors and then see how much error is, how much loss is for that data set. So that's how we define training loss and test loss. So the W that we obtain using the least square method, the ordinary least square method, is the one which give the minimum training loss, right? This is, let's say this is W star obtained using ordinary least square method. So it is the one which gives the minimum test loss, right? This gives the minimum training loss, sorry. But what can we say about the test loss for this W star? What about the test loss? We cannot say, right? So it depends upon the complexity of the model. Complexity means like how which parameter, if we have used linear regression model for, let's say the data set is quadratically related, then in this case it may happen that my test loss is high. But if I, let's say my data set is quadratic in nature and I will use 3-degree polynomial, 3-degree polynomial, in this case my test loss or training loss will be, so it means in this case my the training loss will be minimum, but the test loss may higher, right? In this case, right? So this I don't want to use the terminologies for that. It's for overfitting and one is called underfitting. So that's why, just because there's some trade-off between these training loss and test loss on increasing the complexities uh, and these things. So that's why we using the ridge regressions. I mean, ridge regression or lasso regression. So it makes sure that my model doesn't overfit or underfit in this case, right? So this W star which obtained using the ordinary least square is gives me the minimum training loss. So the one which obtained using this obviously will be is not giving me the minimum training loss. The training loss in this case will be higher, right? So because this one gives me the minimum training loss. But what about test loss? So test loss may decrease. So that is the whole idea about the regression. We want the test loss to decrease down, and we will we suffer some training loss, but that is good for our model. We can suffer some at least some training loss if my test loss decreases in this case. So that is the whole idea of the regularizations for both risk and lasso regularization, right? So remember these things.
One question. So when you define this quadratic and third degree polynomial functions, so you are saying that in case of underfitting, our test loss will also increase, right? With the regularization.
Underfitting is one which is the I mean underfitting is one that model doesn't model is very simple, or say the training loss is high and test loss both are high.
Yeah. So in that case, basically, there is parameters. The regularization parameter won't help, right?
In this case won't help, but if this is overfitting means the training loss is less and the test loss is high. In that case, regularization will come.
Okay, understood. Just one question, sir. Some place I have seen it that raise parameter, it was mentioned as 1 by lambda.
It's just a way how you define it. In this case, whatever I mentioned here, it will be opposite of that. But here we are assuming lambda to be the risk parameter. Or say
Okay. So
regularization.
that's the regularization parameter. Whether it should be 1 by lambda or lambda, it's just the convention, right?
Yeah, it's just a matter of condition I use.
I have a question here. When we are talking about these two losses, regularization parameter and the MSE, should we actually compute the scores, add them up and see, or we actually say, okay, regularization is only this much, and now on the basis of MSE, I will check?
The loss one you are saying?
Yep.
No, so if you are looking for the training loss and the test loss, then you are only looking for the sum of squared error. So sum of squared error, this one x transpose w minus y. No normal class.
Okay. Grade assignment 6, I made a mistake there. I'm just trying to understand what went wrong. That's problem 2. The solution is given, but here is where I'm getting caught. Is the value
sorry, which one, Ravi?
Solution 2. Question 2 in grade assignment 6.
6. Okay. Good.
So in that, you have the omega square, W1 square, W2 square computed. And because W1 square, the threshold is 13, and after that, W2 and W4 only qualify. Then the decision is taken based on what the MSE is for W2 and W4, not a sum. If you take the sum, it comes different.
Okay, so this is not MSE that training that mean scatter. This is the one which we get from the estimated W that we define for estimated W, right? That is defined as that 1 upon what? How do you define that? Sigma square and sum of 1 upon the what we call as lambda vector eigenvalues, right? The MSE for the estimated W.
So, sir, I think the question, even I was very confused. The question is a little like, it's not very clear, because when we figure out which, basically there are 4 weight vectors given, there are MSEs given, and they're saying the theta, which is basically the distance, the vector sum, the length of the vector should be less than a theta value, right? So if you do it, if you calculate the weight vector and MSE consolidatedly, and you take, then you get a separate answer. If you first shortlist by theta, saying only these 2 parameters fulfill the theta, and then look at MSE.
Which question you are talking about?
Second question.
Of the practice assignment or graded assignment?
Graded.
Graded.
Yeah, actually, I also got very confused, Ravi, but I thought first question is also the same. You'll get the same answer as the first one. So
that is where I did the misstep. So it still has been a question as to how to go about with this thing. Actually, that's
okay. Let me look at the thing.
Maybe it's quite trivial for someone who is completely familiar with this, but
No, no,
I
no.
got
It's not. No, no. It's not about. No, I don't think so. It's because if you go by the overall ridge loss function, then it has to be done the way you have done. I think.
yeah.
So that is one thing. MSC is not defined as I mean this thing. So MSC is just only this x transpose W minus y to norm of that. It's not lambda plus W, norm of W square. So I think you
That
are
is
confused with
understood.
this.
That is no. That is understood. That is understood. And the problem MSC is given separately. We don't compute the MSC.
Mhm.
It is the weight vectors that are given 4 different weight vectors, and for those vectors, the MSCs are given separately. If you see the problem, it will be more clear, or the
Yeah.
solution itself.
Yeah. Here, the I think Ravi,
Hmm.
the lambda is not given for us to.
Correct.
I think that's the thing. I
Uh,
think that's the only explanation.
just trying to understand how it is. What is the basis? If we know that, it
So,
better, I guess.
one
Okay.
question, sir. In the ridge loss function, where we take x transpose W minus y norm square,
Huh?
can that be replaced by MSC also? It doesn't matter, right?
Which one? Which you are replacing one?
The see in the ridge one we have
Mhm.
x transpose W minus y norm square
Mhm.
plus sorry, we have the difference plus lambda. I'm now forgetting. So if I
Lambda the norm of W square.
now W square plus the first part is what? Sorry, the first part would be sorry.
X transpose W minus y norm of that.
Yeah, but this is also
This
yeah.
is your
So
MSC. This
yeah,
is your
this is
MSC.
your yeah. This is MSC into n actually. We couldn't. This is not MSC technically because there is we don't
Yeah,
divide it by
mean. Yeah,
mean.
of course. Yes, sure.
Yeah,
So it is 1 by n and mean
we
of
can
mean.
replace it by MSC, right?
Yeah, of course we can replace it.
Okay.
So it doesn't matter if we are minimizing this or we are minimizing this.
Yeah,
It won't
because
affect your final.
it's not dependent on n actually.
Hmm.
Doesn't
So it's
matter.
just a coefficient there, so it won't affect your final weight vector.
Correct. Sorry, Ravi. Going back to your.
Yeah, like, can we see that, or do you want? Should we see that later? I don't know. It's your call.
Question number 2, right?
Question number
Let
2.
me
Yeah.
open that. Let me open that. Someone has asked me on Discourse. I don't remember which question that was. So I'm probably confused with that. So, okay, so here it is given that the value of theta is 13, right?
Yep.
Okay, so this is one which we formulate the. Okay, so if you have remember this thing, right? This particular problem, this minimizing of x transpose W minus y whole square plus lambda norm of W square, right? So this optimization problem, we have to minimize this over the W, right? This problem I can write as minimum of x transpose W minus y, right? Subject to I'm just writing this in another form, subject to norm of W square is less than or equal to theta, right? So
Yep.
this two problems are equivalent thing. So here that problem has been given in this form. So where you have been given that the W theta value is given to you 13. Right now you have to choose from the option 4 which option this norm of theta square is less than 13.
Yeah.
Right?
The
Okay, so
W2 and
what is the
W4
next part?
qualify in that one. Yeah.
Okay, so 2 qualifies for then W2 and W4. Okay, now you will choose which gives the minimum MSE, right? Because your ultimate task is to minimize the MSE. So your optimization problem was this thing. You have to minimize this thing subject to this. So for this constraint is followed by two weight vectors, which is W2 and W4, right? So which weight vectors will give me the minimum one? I will be the solution for this optimization problem, right?
Yeah. I mean, like, where do I read that in the problem is what I'm missing actually. Maybe we can.
Which thing in the question? Okay, let me open the question here.
Yeah.
Yeah. 1 minute. My screen visible now?
It's coming up. Yeah. Yes.
Okay. So in this questions, you have been given this one, right? So
Yep.
you have been given these four vectors, and for these four vectors, you have been given MSE, right? So this MSE for this weight vector, and similarly for all these four vectors. You have been given theta equal to 13. It means that you have to choose weight vectors for which this norm of W square is less than 13. And these two weight vectors, W2 and W4, satisfy this constraint. Right? Now you have to
Yep.
choose for this one, and out of this one and this one, you will choose which gives the minimum square loss. So this one gives the minimum square loss because MSE here is 5, MSE here is 9.
So it's not the total that we compute, is it?
It's not the total, it's the MSE one.
Okay.
Remember the optimization problem. Optimization was what? Minimize the square loss subject to this constraint. Right?
Okay, so we do not compute the total from there. We normally take whatever is there as the minimum of the regularizations and then see what the MSE is doing, is it?
Yes, MSE is doing that. So that optimization can be equivalently written something like this, right? That minimizing of the square loss subject to this constraint, and this constraint is satisfied by this MSE and I mean this weight vector and this weight vector. So your solution will be now this out of this one or this one. So you have to choose which one is giving you the least square loss. So this one is giving you the least mean square loss or mean square error. So this will be your final answer.
Okay, all right. Thank you.
Okay, so now let's move to the second question.
Sir,
Yes.
coming back to today's first questions, one of you made one statement that my training loss may increase, right? So
Yeah.
that don't you think that will be a case of underfitting? If my training loss is increasing, so that's a case of underfitting.
Training. No. So that was the whole idea of the doing regularization. Actually, regularization helps in overcoming the issue of overfitting. Overfitting means where the training loss is minimum, but the test loss is high.
Correct.
Right? So in this case, we don't know why the overfitting is coming from. So the overfitting may be the issues from the complexity. So complexity of the model is high. In this case, what we do, we just or the overfitting can be maybe due to the correlation between the features space, right? So in this case, what we do, we apply the rigid regression or the lasso regression. In this case, what will happen? Your training loss will go up. Because initially your model was overfitting, it means that training loss is very, very low. But what we are doing now, we are compensating on that. It means that we want our test loss to be minimized and we are compensating on the training loss. It may become higher a little bit that we can bear with.
Okay, so our test loss is going down.
Going down. That was the whole idea of doing the regularization.
Okay.
Now the second question is, can rigid regression be used for feature selection or not? So what is feature selection?
Weight vectors.
Weights are different. Like I'm saying, what is feature selection? Features you have like D-dimensional space, so that D are the number of features, right? So what are those? What is the feature selection? Have you come across this term before? Feature selection?
Is used for
Yeah.
lasso.
So even ridge also technically can help, but it's like lasso does it better, but ridge also can technically help. I mean,
Yes,
when you
yes, correct. Yeah,
in a
exactly.
practical sense, when you're doing it, when you use ridge and you're getting some weights coefficients very low,
Yeah.
you can actually omit them and rerun the model. I mean, these are not theoretical things, but practical applications.
Yes.
Basu, but in this course, have we discussed about feature selection till now?
Lasso,
the
yes,
course-
na? Lasso,
Pardon?
yes, no?
Okay.
In course, we didn't discuss feature selection, but this the one thing that you can you should know what is the feature selection and all.
Yeah. So lasso in lasso, the professor in the passing mentioned that is a selection operator, right? So
Yes, yes.
Lasso is selection.
So can this be helped? Your answer was correct that you mentioned that it can help in the. Actually, this is not feature selection techniques, but what RIS does, it's sync your weight vectors to zero. So what we can do, so, let's say you have four vectors W1, W2, W3, W4, and after applying lasso, you come to know that the weight vectors correspond W3, or say this is corresponding to feature 3, this is corresponding to feature 4, this is corresponding feature to and this is feature one. And you come to know that after applying the rigid regression, the weight vector is coming out, let's say 2.3, 0.5, 0.2 or something, let's say 1.2. So you come to know that this weight vector has shrink close to zero. So what you can do, the one which has shrink to close to zero, you can omit those weight vectors and you can choose this. You can select these four vectors for your modeling part. Right. So in that manner, it can help in feature selection techniques. But if I say technically, ridge regression is not a feature selection technique because it doesn't lead weight vectors to zero, right? So if you answer this thing, the answer will be ridge regression is not a feature selection technique, but it may help in selecting the features. And how you will select the one which are close to zero, you just ignore those weights and those features, and the one which are the weight for which the weights are higher, you can choose those weight vectors to learn your model or train your model. Right? So that's how you can ridge regression be helpful in the feature selection technique.
Are that are redundant features?
Yeah, that is probably redundant feature. That is why those weight vectors is going down to zero for those. And the feature selection is one in which we try to select some of the features. We try to get rid of the features which are redundant in our model. Right, so that is feature selection techniques. There are different feature selection techniques, but lasso is one of those which can help in features selection techniques. So the answer for the third question will be yes. Because why it should be, because in this lasso regression, remember lasso always tries to decrease the loss to zero, exactly zero, right? So in this case, if W1, W2, W3 are the W3, W4 are the weights, then in this case, let's say assume W2 has shrink to zero, W4 has shrink to zero. So what you can do, this weight vector has shrink to zero, it means that there is no features 4 and feature 3, feature 2 and feature 4 in your model. So you are only modeling using only those features, that F1 and F. In that manner, lasso is helpful for feature selection technique. Lasso can help in feature selection, and the lasso word itself is coming from that, right? Lasso is least absolute shrinkage and selections operator, right? So selection means that it actually is a feature selection technique.
sir, do we like, how does it exactly do in terms of calculation, sir?
So there is that how it goes to zero. It depends upon the that optimization problem. Remember, the optimization problem was like norm of x transpose w minus pi to whole square plus.
Correct.
Here it is this absolute values of this, right? So this is norm one here. So not square one. It's norm one here, right? So if you look at the optimization problem here in the two-dimensional space, so it looks like something this is square, right? Now
Correct.
we are looking at W here, and which minimizing our MSE. So let's say W star is somewhere here, which is often using, and you have already seen that it lies here. And the optimization technique says that most probably your solutions of this optimization will lie at the corner, these corners.
Yeah. So it tries various W's, which will
Right.
basically
So
the intersection of those ellipses and the
sorry, I'm
the
losing your
modulus.
voice.
I'm saying, sir, it kind of looks for various W's which satisfy both conditions. Is that how it does?
Yeah, optimization problem is looking for in this entire space. In this entire space, looking for different W's, and it chooses one which gives the minimum loss. Right, so most probably it always lies on the corners. So those corners are but where some of the W's are zero, right? So in this case here W2 will be zero, and if your solution lies here, then here in this case W1 will be zero, right? So similarly, if in the higher space, the solution most probably will lie on the edges, these edges. So that's why these weight vectors will go. Some of the weight vectors goes to zero.
So those ellipses indicate, sir? You drew around W.
So
star.
that this was this thing, this like this minimization of the X transpose W minus Y. Okay, so this if you look at W star, so what we remember during the session
Yeah.
we always
But
discuss this.
that's clear. That's the W star. But what do those ellipses represent?
Ellipses are looking, so this was the W which was giving me the minimum loss, right? Minimum MSE. Now we want going far away from that, but actually we don't want go far away from that because this is the minimum loss and we want to retain that as well, and we are also constrained that our W star in this region. So what I'm looking at the W star in this region, which is closest to this one, right? So those ellipses are one which actually is are coming from this. But if you solve those,
Each ellipse is a W basically.
each ellipse is not a W. It's like that. If you remember that problem, like we are looking for W for which this FW is FW star plus that some C, right? So for that is coming from that ellipses, right?
Okay.
So this one, if you solve this equation, that is coming out to be ellipses.
Okay.
Okay, so if you go to the next question, okay, you can read out these solutions later. Okay, so one more thing that we didn't discuss in the lectures as well and in the session as well. Remember in the week 5, we were saying that our model need not to pass through the origin all the time. And in that case, what we do, we actually add the interceptor interceptum in the model, and corresponding the features we add as a dummy features, right? So our weight vectors in this case become, your matrix will become D plus 1 times n matrix, where we add one column which is your dummy feature, right? And your D vectors become your D plus 1. So in this case, the you add W0 as well in your model. So your model is W1x plus W, or say F1, W2, F2. So you add interceptum as well, just because your model need not to pass through the origin in this case. So my question is that do we penalize the interceptum in the ridge or lasso? Do we penalize this W1, W2, W1, W2, W3, right? We want to string them to 0. Should we penalize W0 as well or not?
No, we should not.
This intercept will be Y intercept, right?
Yeah, by intercept.
No, we don't penalize the.
Yeah, so always remember, whenever you're trying to formulate the problem of phase degree or regularization, your this is your X transpose W, right? X transpose W minus Y whole square. So this here I'm W taking as W0, right? So I'm adding that intercept as well. So this thing I can write as lambda. So in this thing, you have to omit that W0 as well. So right, if this is not summation, if I write it that Wi equal to 0 to n, this will become W transpose xi plus Wi transpose xi plus yi to whole square, plus this will become lambda summation over Wi square. So here I should start from 1 to n. Remember, this should not start to 0. It means that you are not penalizing W0. What if I penalize W? What will happen? Remember your model, let's say your data set is coming somewhere here, and your best fit model is somewhere here, right? So here it will be W0, right? So this length will be W0. But if you penalize W0, it means that your model should, let's say, W0 penalizing and W0 coming out to 0. In this case, what will happen? Your model will must pass through this thing. That should not happen, right? We want that model should pass through this point, this intercept. That is why we don't penalize your W0 level. So always remember, in the formulations of ridge regression or any lasso or regularization, we never penalize your intercept. We only penalize these W's. Okay.
Sir,
Just
sir. Yeah, I think in second line, D belongs to R to the power D plus 1 should be. It is not D into 1, right?
Sorry, yeah, D plus.
Yeah, it is D plus 1. Yeah. Okay.
no, when we don't penalize that, what does it mean? Like, it doesn't go up, the intercept remains the same. That is what we're saying.
Yeah, this intercept remains the same. We are not sending it to 0. And even if you think that W star is nothing to do with any features, right? Only these weight vectors W1 to WDRs, one which are associated with the features, right? So this W0 was associated with the dummy feature, so you can say that it has no correlation with any of the features, because its values is one for all the training data points. So it has no correlation with any of the data points. So W0 will never penalize this feature as well.
But doesn't it mean that I'm actually holding the line at one point and trying to rotate it?
Yeah, that's it. So W0 it will be learned using the model, right? So the best fit model can be any line from this space. So the model itself will figure it out which W0 will be suited for that. And for W0 now you are penalizing other weight vectors. So maybe you are trying to decrease your W1 and your I mean the line may be something different than the best fit line.
Sir,
Yes.
just a small doubt, sir. Let us go back to that slide only. The previous, yeah, here itself. This has nothing to do with concept, sir. This is just to do with notation. I will just take less than 1 minute. Sir, like whenever we are trying to find out y, so sometimes we are writing W transpose X, and that is clear to me because W transpose means we are writing W in the form of row vector, and then X is in my column vector. So I am getting my Y, right?
Yes.
But again, then sometimes we are writing X transpose W. So both of them mean same, right?
So this X transpose W.
Yeah.
Yeah, this here GP is X transpose W minus Y. Here it's a matrix notation.
Okay, it's a matrix, no?
Yes.
Yes.
There
That
it
was
is
my doubt.
individual. There it is individual elements and columns. Columns and rows.
So here we are transferring all the data point into row vector, right? And then W as a column vector, right, Vasu?
Correct.
Yes.
Correct.
Yes.
So here T will be N cross D.
Correct. So sir,
Sorry. Hello.
does it include W0 also here, sir? That dummy feature?
In this particular thing.
Yeah.
Yeah. Here we are reading W0. Here it start with 0, and here it should start from 1.
Okay, and then we are squaring it because after subtracting it, we are getting the length of error, right? So we are squaring it because that is square of the error, correct?
This is minus. Yes. This
That
is the
is
error, right? This is the
square.
prediction, and this is the actual value.
Even in the previous line also, sir, X transpose W minus Y. So, yeah, previous line only. Previous, here itself, the second last line, X transpose W minus Y. Norm is square. So the norm is basically the length of the error because after subtracting Y from X transpose W, we are getting that Y error, correct?
Yeah, error for all the data points.
So we are squaring that, right?
Yeah. So here, remember, this will be a column. This is again a column. So here is the prediction for the first data point. It's the actual value for the first data point. The prediction for the second data point is the actual value. So take the differences and then the square thing.
So my answer is a column vector, and then I am taking the square of the norm of that column vector.
Yeah.
Right?
So norm, what will do? It will take the square and will sum over those values. So it will take the difference here, will add those, right?
And square of the norm is nothing but the dot product of this vector. Huh? Like
so X transpose W will be this thing. So difference of this, difference of this, difference of this, difference of this, right? So what is norm? Norm just will do the square and will add those things. So this is the same thing like this.
So is it right to say that square of the norm is nothing but dot product of the vector with itself? Because when we
that's how you define your norm in the standard inner product space, right? So norm of W you define as W transpose W.
Yeah, so that's the reason when we are removing that square, so we are writing X transpose W minus Y into X W minus Y, right? Sorry, X transpose W minus Y whole transpose into X transpose W minus Y.
Yeah, so this thing you can write it as X transpose W minus Y transpose X transpose W minus Y, same thing.
Okay, sir. Thank you. Sorry.
The arg function, the loss function you've written below, it should be I is equal to 1 to N only because it's summing over all the data points. you're not summing over D.
I2, 1, 2. Okay. What?
D only, not N.
No, you've written W1 x1 my transpose minus y1 square plus lambda wi square, right?
Okay, so this should be W transpose xi minus.
No. Yeah, that's fine. The summation should be 1 to n.
1 to n, yeah, of course. So in this case,
it had W0 also, no? That's the reason why he had written.
No. That is correct. This is correct point. So this should be I equal to 1 to n. Here W vector should be W0 to WD. And here we are taking data points. So that is the correct point. Yeah. Right.
Yeah, and there in the next term it is from W1 to WD.
Yeah, here it is W1 to WD. Yeah, correct. Right.
Sir, no, this point is not clear to me, because when I am taking a dummy feature, I am writing it as x0, right?
Okay, so
in that case, ideally, I should start from I0 to I.
Okay, let me rewrite it again. I just made a mistake here. Let me rewrite it again. So what's here? We loss function in the rigid regression where we are adding dummy features will be here. I'm taking W transpose xi minus by I to whole square and sum over all the data points. So here I is actually corresponding to data points, and here I'm adding lambda and summing over W. So here I is actually corresponding to the weight vector. So, or you can even include some different index here. So let's say J here, J1 to D.
But sir, you're taking W0 also, na? And you're putting a dummy feature x0, right?
Here W I'm calling to be W as W0 to WD.
Okay, got it. My data point are from 1 to n only. Yes,
yeah, data points are 1 to n. Here I is corresponding to data points, here and J is corresponding to W. So that's the.
Sir, but then the dot product doesn't make sense. Like in W we have n plus D plus 1, right? If
so here so here it is D plus 1, and in Xi we have added dummy feature which is 1 as well. So Xi will become.
So both in W as well as X we have added dummy features, right?
In W we don't add dummy features. W we add W0. This is intercept term.
No sir, we add a dummy feature, na? W0 multiplied by x0, and we assign the value 1 to x0.
So yeah, x0 is 1. So this is your feature, dummy feature. This is set at 1.
So that's what he is saying. Service is saying that in that case, dot product will not make sense.
Because because if we don't add dummy in W, then it would be a dot product of D and D plus 1 vector.
Correct.
So that doesn't make sense.
X is also D plus 1 into n matrix now.
No, but here in this particular formula, xi is just a vector, right?
Yeah, and xi is a vector, correct?
Yeah.
Yeah, but that xi is a vector which has D plus 1 dimensions is what I'm saying.
Yes, that's right. But if we do, then W, we need to add one more dummy feature, right?
There is no dummy feature. W here is a D plus 1 vector, which is W0 to WD.
Yeah, that W0 is a dummy feature, is what I'm saying.
No, it's not a feature.
It's a weight vector. It's not a feature matrix. It's a weight vector. X is a feature matrix.
Basu, he is saying that we are assigning x0 with W0, na? W0 into x0, and we are putting a value of 1 in place of x0.
Okay, so why you are calling it a feature? W is not a feature.
Sorry,
W is weight vector, no?
So that extra term, sorry, I misspoke on the terminology. So W is that extra term, and X is the X0, I think, is the weight dummy feature, right?
Yes,
X0.
X0 is the dummy feature. X0 is the dummy feature.
Thanks.
Actually, all this is, if you remember, I also was initially confused. If you go back and look at polynomial regression in MLF, it's very clearly taught.
That week 3.
Yeah, it's very clearly explained how you do that, and right. So if you just refer to that, it will be clear. And what Sarvesh said is absolutely right.
Okay, so you have already studied this in MLF.
Polynomial regression, yes, but not this one, ridge regression. But when you do the polynomial regression, like when you do there we also took basically it's whether have you taken the intercept or not. When you take the intercept, you need 1 right? Otherwise you don't.
Okay, so the idea is simple, right? So the answer is for this question will be, we never penalize the intercept for rigid regression or the lasso regression, right? You can read it out. Same thing. So what are the limitations of rigid regression and the lasso regression?
Cannot have closed form solution.
Yeah, lasso doesn't have closed form solution. That is one. Yeah. This one. This.
It is not differentiable function.
Yeah, lasso is not differentiable. That's why it not have a closed form solution. So you can read it out. It's very. I mean, it's very practical question. Need not to have any standard answer or any unique answer, but depending upon the solution, it may have the problem, right? So it's a sensitive to outliers. It means, let's say your feature is something, one feature is taking very high values. In this case, what will happen? Your weight vector corresponding to may be higher or maybe low. So in this case, that outliers will affect your weight vectors, and your lambda values will be will be tuned according to that. So that is the one case. In this case, your model will be affected by the outliers. And another thing is, you need to tuning your parameters in this case, right? So this will increase your computations cost for your model. So this is some of the limitations for the rigid regressions. And if you refer to some books, you will find there's many limitations of for both rigid and lasso regression. So this is the one that I've noted down here. You can read it out and you can figure it out what the possible limitations with this rigid and lasso regressions. Okay. So if you move to the so this is very practical question. Need not to have any straightforward answer or any unique answers. Depending upon the solutions, the problem you are handling with.
Yes.
You may have different answers to that. So
answer is yes. In general, it's yes.
Okay, so in general, how do you handle the missing values?
That's the same thing, Laplace smoothing.
Missing data means like.
You mean data is missing? Okay.
Data is missing.
There are many other techniques like mean imputation and median imputation, all those things.
Yeah. So,
we adding two additional data to the training set, right? One containing all zeros and other containing all ones.
That is not missing data problem. Missing data means that let's say you have in the training data set, you have some features missing values there. So if you work with a practice in real world data set, you will find that in the data some values are missing or somewhere.
One approach is mean imputation, like we take the value mean and put it there.
Yeah, so imputations, those techniques are called imputations. You impute some values for those missing values. So this is very general problem, and this is very, this is the issues that we handle when we pre-process our data, and pre-process is very important part of any machine learning model. So one of those pre-processing part is your imputing, how you impute your model, the missing value. So in what we do in let's say you have a categorical feature. So in this case, what you can do, you can either impute the mod values as well, right? So because in the categorical you don't mod values, right? So let's say in the Bernoulli knife base, you have 1 and 0s for the feature. So you just check which one is the which is the mod for this particular feature, and you just impute the values for the missing data. Similarly, if you have categorical, the numerical feature, in this case, let's say you have applying Gaussian knife base, and you come to know that for some feature f, let's say f1, you have numerical feature and some values are missing. So what you will do, you just you take them average or say median, and just impute that values to that missing value. So those are the imputation techniques that be very important at the time of pre-processing. Otherwise, your model will not be that accurate if you don't handle your missing values. So
when we will learn all those techniques, are in MLT or what, sir?
In MLP, where you will start training your model, you start building your models on some data sets. So where you will see that this pre-processing part is very important.
From scratch,
one of those is So there's one of those is called imputing the values, right? Okay.
Sir, it's called feature engineering, right? This when we deal with this missing values and all. Or is it different?
Feature engineering is very not a different one. Like how which features to select and which features to drop out. You can call it as feature engineering, but in machine learning terminology, we call it pre-process your data.
Okay. Okay, thanks.
So whatever limited knowledge I am having, I think feature engineering is different. Feature engineering means, say for example, just a very trivial example, both distance and time is given, right? So I will divide them and I will take speed. So now I have created one more feature and I will remove those two features. So that is
Yeah,
called
so
feature
that is
engineering.
how you select
Yeah,
your features, which
yeah.
features will be.
In a very layman terminology, that is called feature engineering. Yeah,
Okay, so
sorry.
feature selection is feature engineering.
Feature selection and feature engineering still are two different things, but somehow
Okay.
related. Somehow related. Sorry to digress. Sorry.
Okay,
So
so
basically, anything to do with you transform certain features, you create new features, you
Yes.
drop some features, right? All that comes under feature engineering,
yes, yes.
right? You calculate new features, like for example, age is given, you take average age or something like that, or date of birth is given, you extract age, or all kinds of things, right?
So let's not move into that direction. We just will end up doing something else. So let's stick to whatever is here, right? Okay, so that's the another question there. How does the choice of distributions affect the performance of the naive model? Right. So remember how you choose the distributions which naive you will apply, whether Bernoulli or Gaussian.
In case of when the features are binary, we use Bernoulli, and when the features are reals, we use Gaussian.
Yeah,
Naive.
exactly. Yeah, exactly. So you look at the distributions and type of features. So if your features are categorical features, I mean the binary features, then you probably will choose the Bernoulli naive Bayes. And if your features are numerical, then again you will choose Gaussian again. So there's only two standard, not these two standard. There are many other naive Bayes algorithm as well. But one is called multinomial, where your features are categorical, but it takes more than two values as well. And Laplace is one which are skewed, kind of Gaussian, but kind of skewed, right? So you have to look at the distributions, and according to that, you have to choose your which model you have to apply for your particular problem, right? So that is the
Sir,
one
but
task.
but what if the x by y follows a not a Gaussian distribution, but let's say it follows an exponential distribution?
Exponential distribution.
Yeah, I'm saying, is that a possibility at all?
So exponential, if I remember correctly, exponential comes from some family. What is that family called?
Exponential comes from.
It is standard member for any standard family. I mean, I don't remember the name, I think. So exponential is lambda raised for minus lambda x, right? Where x is greater than 0
Yeah.
and 0 otherwise. So what is beta? Beta is
No, it's from the gamma distribution family.
okay, yeah, gamma. Gamma is defined as e raised to power minus. So
Uh,
gamma, in this case, you can apply gamma, and what is gamma? E raised to power minus
gamma is
alpha x, right?
yeah,
E raised to power minus
alpha minus 1, and then I forgot actually.
whatever that is. I don't remember the exact PDF for that, but it's something like e raised to power minus alpha x, and here's some constant. Constant is in the form of gamma function of alpha, right? So this is the gamma distribution, and the exponential is the part of that family. So you can apply the gamma distribution in this case, that case. Okay. So
Okay. You're
okay,
saying the general family distribution needs to be applied.
need to get like names.
Okay.
So before choosing which one which naive Bayes you are applying, you have to look at the features. How the features are they categorical, are they numerical, and are the mix of those, or say Gaussian distributions you have to apply. And in the Gaussian again, it can be skewed kind of thing. So in that case, Gaussian may behave badly. So different distributions you have to look for, and you have to apply on that, right? So this is all things that you have to choose before applying your actual model, before training your actual model. So these all things that will be very clear when you will start modeling your actual models or building your actual models, right? So these all ideas will be handy in that things. So can KNN be used for regression problem? Okay, so yesterday we discussed about the naive Bayes. Naive Bayes cannot be used for regression problem. But yesterday, I think I saw in some post that for some of the techniques, knife-based, Gaussian knife-based is used for the regression problem. I didn't go through the entire paper for that, but in some tasks, regressions problem can be handled using the Gaussian knife-based as well. But for now, you just assume that for knife-based regression, knife-based cannot be handled for regression tasks. Okay. So this is next question. Can KNN be used for the regression problem?
Yes, it can be.
And how will you use
We
regression?
would consider the average of the k nearest neighbor as the predicted label.
Yeah, right, exactly. So in the classification, what we do, we just take the majority to make the predictions for the out of the k nearest neighbors. So in the case of regression, we take the average of those k nearest neighbors, and that's how we make the prediction. Right. Okay. So these are the some questions that I prepared for, and
Sir, I think questions are done, right?
yeah, mostly done. So
Yeah,
these are
sir.
questions you can check it out.
Okay.
Those are out of the syllabus. It's not covered in the syllabus, but just the good time that you can look for what are those how the feature selection is different from dimensionality reduction. So one of the techniques that we studied in the dimensionality reduction was PC, right? And feature selection there are many techniques for feature selection. So what is the difference between feature selections and the dimensionality reductions that you can check it out? What is the curse of dimensionality? You must have listened to this term, right? Curse of dimensionality. And so what is
Yes, in
this? How it
KNN we
applies?
come across this.
Okay. And how you handle missing values in general, and how does the increasing of size of training data will always help in improving the performance of the model or not? Right. So these questions you can look for by yourself. And or can L1 or L2 regularization. So this is your lasso one, and this is your this one. So can this regularization be used for decision trees or not? Right. So this answer I want you to figure it out, and it's just out of the syllabus. We won't ask such questions in the quizzes or somewhere. But for knowledge, for your sake of your knowledge, it's better to know these questions as the solution.
Sir, we will upload this document, no?
Yeah, I'll upload this document to you.
So what was the last question?
Last question, this one, KNN.
No, sir. In the last list of questions, can
So
L2
this is, can L2 or L1 regularization be used in decision trees?
Sir, I was trying to say, like when we asked that whether KNN can be used for regression or not, so it will be better if you can throw some light. Say for example, between supervised and unsupervised, the difference is very clear. Unsupervised not having any label, and supervised techniques are having labels, right?
Hmm.
So the moment the label is a continuous, like in regression, correct?
Yeah.
So when y is continuous, then we are calling it as regression.
Yeah.
And when y is some sort of discrete kind of thing, like we are classifying between two groups, like red group or white group and all those things, then it is falling in the category of classification, right?
Yes.
So then again, why we are bringing down this question, like whether knife base can be used for regression or whether KNN can be used for regression, because when these are meant for different purpose, they are completely meant for discrete kind of classification, right? Like say for example what Sarvesh said, okay, that is making sense, that in KNN what we do generally, we take the, what is the maximum number, whether 0 is maximum or 1 is maximum in the nearest neighbors, right? So what he said that okay, I will take the average. Say for example 10 data points are there and 6 are 1, then I if I understood it correctly, then he said 6 by 10, so it will be 0.6 will be my output. Oh, that's what he tried to say, right? But then what will be the accuracy of that model in this case? Because the model is meant for something else and we are
Okay, so in
utilizing.
that case, so yeah, so in this case,
Hope you got my question. Hope you got
yeah,
my
good.
question.
I got your from, you are confused with how you can use same algorithm for regression
Yeah, when
classification, right?
they are meant for different purpose.
Okay, so it's not like they are meant for different purpose. The algorithm is same. So only remember this thing: the loss will change or the evolution things will change. In the regression, if I take regression and classification, so in the regression, loss function generally sum of squared error or mean of squared error, right? Here we take
Or even
how to
root,
define loss,
or even
cross
sometimes,
sensitivity,
or even sometimes we take root mean square of error, because to
whatever
control
that is, whatever that is.
to match the unit, to match
So
the
here
unit.
evaluation we take mean of squared error, and in the classification we take evaluation as the accuracy or precision or recall, whatever that is. Accuracy generally or precision or whatever. Like so, like let's say about decision trees, right? So decision tree can be used for both classification and the regression. So in this case, how you split for the classification? You take entropy, right? Entropy as the measure.
Entropy, Gini, and yeah.
Gini index or entropy, right? But in the case of regression, you choose that measure as a sum of squared error, right? So only thing is that the loss function or the measures changes, but the algorithm goes in the same manner. Similarly for the KNN. So KNN, what we do, we make the predictions. So here we do what we do, we choose the k nearest neighbors, right, for the particular data points, right? And out, let's say this is your data point that for that you want to make predictions. You look out the neighborhood. Let's say you are looking out in this neighborhood and some data points come out. If this is classification problem, then we take the majority of these things, and if it is a regression problem, then we take the average of these things. The algorithm is same, but only thing is that in the case of classification, you are taking the majority, and in the case of regression, you are taking the average of those data points, the labels of those data points.
That's what I said. Now, say for example, 10 points are there. If the value of k is 10, right? And the majority 6 points are falling in one category, so I will take 6 by 10, right? That's what we mean by
that will be accuracy for that.
6
Not
by 10.
accuracy. I
No,
mean,
that will be the output, na 6 by 10.6.
no, not 6 by 10. If it is a classification problem, let's say six
No,
six
if
long.
it's a classification, then I will say 1. Then I will say 1. If 6 points are
Yeah.
belonging to 1, then I will say 1. I'm saying when it is being used as a regression, then what will be the answer? 0.6 or 0.4?
No. So in this case, these labels are not categories. In this case, some values, let's say 1.2, 1.5, 0.8. So these 10 data points will have some label associated with those values, right? So this by 1 up to by 10 will be some value. You take the
Okay.
average of these things.
Okay. In that case, it will not be level 0 or 1, right?
No. Now this otherwise it's not a regression problem, right? If they have labels,
Mhm.
I mean they have classes as labels.
Mm. Okay.
Okay, so have you listened of these evolutions? Accuracy, precision, recall.
Yeah, I think this will come in logistic regression, right?
Not.
Hello.
Yeah.
I
So
think this
accuracy.
accuracy, recall, and precision. I think it will come in logistic regression.
No, explicitly sir didn't mention in the lectures, but it's better to know what these are. So accuracy is one. Let's say you have 100 data points, right? And your predictions, accuracy, these are defined for the classification task, not for the regressions. Okay, so out of 100, you are making predictions for 100 data points, and out of 100 data points, you are making 60 correct and 14 correct. So in this case, accuracy will be 60 by 100. Out of total, how many you have predicted correctly, right? And precision is what? Out of total positive, I mean, how many out of total predictions that you have made, how many are correct things, precise, how precise this your model is, right? So that is how you define the precision, and you define like true positive and true negative and false positive and false negative, right? False positive, that which are predicted to be positive and actually they are positive, so they are true positive. And false positive, which are predicted to be positive but actually they were negative, so that is called false positive. And true negative was which are predicted negative but truly and truly they were negative, and so this is true negative. And false negative, which are predicted negative but they are actually positive things, right? So precision will be defined as how many are defined correctly, how many are defined correctly, true positive, right? So uh, this will be your uh, mm, this will be true positive, this will be true positive and plus false negative, right? So this is what, so this is the total which are defined to this was, sorry, false positive, this is false positive. So these many are defined to be positive, but out of these only these were the truly positive. So this is the precise, how precise your model is. Recall is one which are actually positive, and out of those positive, how many your model has decided predicted correctly. So this is true positive plus true, this will be your false negative. So in this case, these are the ones which are truly positive. These are the truly positive, right? And out of those, you have correctly predicted this one. So this is recall. This is precision.
No, I took the name of logistic regression because I have taken business analytics. So this concept was explained in logistic regression.
In general, it's you can apply for any
classification.
not
Yes.
just this.
Sir, can you just summarize once again, sir? The first one is clear. Accuracy is clear.
So
Sir, can you just go back to the
another one is precision. Precision is how precise your model is. Precise is in the sense that let's say you have make prediction that out of 100 you have make prediction that 60 you have predicted to be 60 predicted to be positive class, right? You predicted that 60 belongs to positive class.
Correct.
So out of those 60 that you predicted positive, how many are actually positive, truly positive? I mean, the true labels are positive. So the true positive, I mean, they are predicted to be positive and truly they are positive. And how many are predicted to be positive? This is the true positive of something is false positive. I mean, though you have predicted to be positive, but actually they were not negative. It's negative. So this how precise your model is. And one is recall. Recall means out of total bits in the training data set. Let's say, so you have, let's say in the training data set, you have 70 positive and 30 negative. And out of 70, your model is recalling to be, model is predicted to be 60 positive. So 60 out of 70 is your recall, right? So this is your true positive, and this one was that actual positive. So true positive that and ones that you have predicted negative, but actually those were positive. So these are the total positive in your data set, right? So how many you have recalled from your data set?
Okay.
It is called recall.
Okay, got it, sir. Clear.
Okay, so I think that's all from my side. If you have any doubts in any questions, you can ask. Otherwise, we can.
Practice assignment 6.
Practice assignment is question number
5. Actually, do we have the relation of lambda and W weights? Because when lambdas increase in the problem, I'm not getting exact calculation. I didn't get it. The fifth question.
when lambda increases, your weight factor sinks to zero.
Okay, but in how does 1369 the answer? How do we get it? Any?
So you have to choose. You have to look at the options. So other two options are actually more than initial weight vectors.
Okay, that is not just a conceptual, right? We are not actually.
Just concept. You have to look at the options and you have to choose the
that I got
best
it.
one.
I thought any other exact calculation is there.
No, exact calculation you cannot do here.
Yeah. Okay. Yeah. Thanks.
Can you repeat this last bit about precision, prediction, and recall once again, please?
Okay, so precision means what? How precise your model is.
Correct.
Right? So let's say you have 100 data points. 100 data points, you are making prediction for these 100 data points.
Yeah.
Right? And assume this out of this 100 data points, the 70 was positive.
30 is negative.
And 30 are negative. So these are the true labels.
That is a true label.
Okay, so let me wait.
Sir, make a confusion matrix, then things will be clear.
Okay.
Shall I just tell whatever I understood? I think in precision, we are calculating for false positive, and in recall, we are adding that false negative, right? How many we have falsely considered as negative points, right? That is the only difference I'm seeing.
In precision, in the denominator, we are taking false negative.
No, precision false positive.
That is precision.
And in recall, we are just calculating how many negative we have taken as a false negative.
Is my screen visible? Whiteboard?
Not yet.
Now it is coming.
Okay. So assume if you have in the training data set, you have, let's say you have the data set, you assume that you have 100 data points, right? Now it's fine. Okay, so you have 100 data points total in total, right? N equal to 100. Out of 100, 70 are positive class. These are the true levels, and 30 are the negative class. So these are the true levels. Okay, so these are the true levels. Now you have used a model and you predicted 60 to be positive and 40 to be negative. Right, out of this 60 you have predicted are actually coming, let's say 50 are coming from the 70, right? So here it is 50 plus 10. So out of those 70, 50 you have predicted to be positive, and out of this 10 negative you have predicted positive, and here you have predicted how many, 20 plus 20, right? So these are actually, so what are these? These are true positive. Actually, their labels are positive, and you have predicted positive, and truly they were positive. And these were predicted to be positive, but they were actually negative. So these are false positive, right? So you have predicted positive, and but false prediction you have made
Okay.
because they were actually negative. Similarly, this is predicted to be negative, but actually they were negative, right? So these are true negative. And in this case, these are, you predicted them to be negative, but actually they
False.
were
They're positive. Yeah.
positive. So you can call it a false prediction, right? A false negative. So if you make the confusion matrix like that someone mentioned, true positive, false positive, and so this is true positive. Okay, so or you can call it positive negative, positive negative. So this is your true labels. Let's call this. These are your true labels. This is your predicted labels. Right. So how many here? How many will come? 50 will come here, and true is negative, and predicted to be positive. Here will come 10. Here it will come 20 and 20. So if I say accuracy is easy, right? Accuracy is one. Out of total, how many you have correctly uh, uh, predicted, right? So these 50 and these 20 you have make prediction correct. So this
100,
70 item 100. What about precision? Precision is one. Uh,
True positive.
60 by
True positive
so
by true positive plus positive.
precision is whatever you have make prediction to be positive. How many are actually positive?
50,
So
right?
you have make say 60 to be you have predicted to be positive, but out of those 60, only 50 were truly positive. So the precise, how precise your model is. This is 50 by 60.
May I
Right?
ask a question here? Sorry, may I ask a question here? On the negatives also, we predicted 20 of the 30 as negative. That is also correct, right? Why are we not including that?
These are predicted to be negative. These are predicted to be negative. I'm only considering those which are you have predicted to be positive. You have predicted these 60 to be positive.
No, okay. Precision as a term, as you are just mentioning a
Ravi,
little earlier.
Ravi,
Yeah.
your question is very valid question. Right now, whatever we are calculating with respect to positive. And in
Okay.
question, it will be clearly mentioned that whether you are calculating all this terminology with respect to +1 or 0, means positive or negative. So that's the
Okay.
reason why sir is taking only positive. Your question is
No, in
absolutely
general,
clear.
precision is defined only for the positive class.
That's fine, sir. Fair enough. Fair enough, sir.
Okay? And another that you define as a recall. Recall is one out of total which are truly positive. How many you have already recalled them? So recall them, you have predicted positive. So you have predicted 50 out of those 70, right? So this will be a 50 out of 70. Okay, there is one more measure which is called F1 measure. This is harmonic mean for precision recall. This is harmonic mean of
1 minus, right?
harmonic mean of precision recall. So this is, you can think as 2PR upon P plus R.
Sir,
1
harmonic
minus,
mean of
right?
precision and
Precision recall. So there is always a trade-off between precision and recall. When precision increases, recall decreases. So that is why we choose F1 measures. So this is harmonic mean, right?
what is its significance, sir, for F1 measure? What is its significance? Because accuracy, precision, those terms are clear. What is the significance of F1 measure?
F1 measure, because there is a trade-off between precision and recall. There may be some case that precision is 0.95 and recall is 0. Very less. There may be some cases like, let's say 0.05. So it may be, so if you choose precision, then you have misleaded your model that your model is correct, but actually your model is not correct where recall is very low. So just because there is trade-off between recall and precision, we take Eban measure, which is harmonic mean of precision and recall. Right? And so you can read it out and you can check these question as well. Why we choose Eban measure and Eban measure as a harmonic mean, why not the geometric mean? So why as a harmonic mean? Why not? Why not as a the simple mean, right? That average of precision and recall. So you can try to find out the answer of that, or even one question that you can try to find out that why accuracy is not a good, why accuracy is not a best choice always. Where accuracy will fail to give the best choice for evaluation. It's not a bad choice.
Where do we apply all these? This accuracy, precision, recall.
These are the evaluation measure where you evaluate your model. So this in the classification.
Whenever you can't commit type 2 error, accuracy will fail.
No, accuracy will fail in the case of class imbalance.
Correct. That also, and when correct. That's correct. Huge class imbalances, accuracy will fail.
So in that case, accuracy is not a good measure. That's why we go for the precision and recall.
Yeah, in fact.
So these which measures to use depends upon the problem at hand.
But type 2 error is will also play a role, right? Because we can't have too many false positives.
So type 2 error is one which you predicted positive, but actually they were not. No. This is type 2 error, right? So type 2 error was which you predicted negative, but actually they were positive, right? So this is called type 2 error. So this is your associated with the recall.
False negatives. I'll work it out. I don't remember. Type 2 I thought was false negatives basically.
Right. So these measures depends upon the problem at hand. Let's say you define a problem at you are diagnosing some disease. Let's say you have modeled something that detects the cancer, right? So this is your model. So cancer, there is cancer or not. So in this case, what you want to use, recall or precision?
I think we should go for precision.
Because we want your model to be precise, right?
Yes.
Whatever you predicted positive should be positive, right?
Yes.
It's not like, so this is, in this case, you probably will prefer precision. So it depends upon the problem, what problem you are working with. Recall is something like, let's say some, what problem should be here? Because where you want most of the positive to be predicted to be positive, right? So you can think some problem in some sense, like you always want all the correct one to be with your side. So in that case, you will use recall rather than precision. So, okay, and you can even come up with some examples where precision is high and recall is low, and so.
Sir, I am not able to comprehend. You said that there is always a trade-off between precision and recall, right?
Yeah.
But ideally, they should move in the same direction. If I am building if I am building a very good model, where my accuracy is very high, so ideally both of them should move in the same direction.
No. It need not to be true, and generally there is trade-off. That's why we go for F1 measure, and you can even think of why it happens. Like there is
that's why I'm bringing accuracy also. No, that's why I'm bringing accuracy also in picture, because if accuracy of my model is very high, then both my precision and recall should also move in the same direction. Because
no, it need not to be true. It need not to be true.
Okay.
So you can read out about these things. We didn't discuss explicitly in the lectures. That's why I'm not going in the details. But
no problem.
If we consider a case where all the data points, like there is no false positive or false negative values. In that case, both precision and recall would be 1, right?
Correct. Even accuracy will be 1. Will be 1. Yes.
That is the ideal cases.
From that logic only, I was telling surveys that
those are the ideal cases that we don't consider.
Yes, but here in this case, both are 1, right? So like it's not like if one is high, other is low.
No, correct. It need not to be true always, but in general, there is a trade-off between precision and recall.
Okay.
It's not that always should go in the opposite direction. That need not to be true.
Okay, okay. Thank you.
Okay, so I think that is enough for today's session. I was hoping that you will ask me week 8 questions, but mostly on week 6 they were. Okay, that's fine. Week 8 was simple enough. Okay, so I think we
Problem
should
is
wrap
that
up now.
problem is that most of us are still struggling with that mathematical symbols and notations only.
So that what we can do for that.
You
Week
can't do
eight,
anything. That we have to
week,
suffer on our own and
week 8,
figure
I
out.
do have a request, sir, but yesterday you said you'll take, like, you can't do it in one day, but later on, maybe during quiz time or later if we have some time, if
Yeah.
you can
So
build
those
some.
two line actually I am not familiar with, so I have to learn and then only I can come up with
Okay,
those
okay,
things. Right?
okay.
Otherwise, I would
What,
have definitely prefer those things.
what, sir? What?
No, I was saying those,
Visualization tools, right?
yeah,
Yeah, yeah,
visualization of
visualization tool.
some
Yes,
of
yes.
those Gaussian distributions, those ellipses and all, contours, and even if, sir, is it possible for somebody to, like, I had requested in Math 2 also, but it didn't happen. Like somebody who can teach us GeoGebra, where we can do some of these.